this. What is going on? Is there work being done? Yes, there's work being done. Okay, how do we know there's work being done? It's accelerating. Okay, well, I mean slowing down. It's accelerating negatively, but it's changing its velocity for sure. Okay, if there's a change in velocity, what kind of energy is changing? Kinetic. All right. So we know that the work that's being done by the car's brakes is going to change the kinetic energy of the car. Everyone with me there? Okay. So that's how we got to set this up then. All right. We know that this is a work energy theorem problem. Work's a change in energy. Okay. Our givens are that we know the force. Okay, 10,000 newtons. Okay, and it slows from 20 meters per second to 6 meters per second. Okay, and the car's mass is 1,700 kilograms. All right, how far does it travel? Okay, formula for work? Work is force times distance. Okay, and that's going to mean the final kinetic energy minus the initial kinetic energy. Okay, something that we haven't covered with this. Force is a vector quantity. Okay, the car is going to travel forwards while it's slowing down, agreed? But in order to make it slow down, the force exerted by the brakes is actually which way? Backwards. So, if I want D to come out with the right vector, that would be forwards, I need to make F negative, right? I need to make it backwards, right? Because when I do this on this side, my final kinetic energy is a smaller number than this one, isn't it? It was going faster in the initial spot and slower here. If I don't make sure that F is negative, D will come out negative, which means as soon as I slammed on the brakes, the car started going backwards, which obviously is not the case, okay? It is going to accelerate backwards, but it's not going to move backwards, and that's what that answer would come out and say, which is not the case. All right, so we got to plug in our numbers here. If I want to solve for D, what do I have to do with F? All right, move it over to here. So I'm going to have this. D equals 1/2 mvf squared minus 1/2 mvi squared over F. Okay, so I've just plugged in the formulas for kinetic energy there. Okay, can I just plug in my numbers now? Yep. All right, so we're going to have that D. Okay, D is going to equal 1/2 times 1,700 times 6 squared minus 1/2 times 1,700 times 20 squared divided by negative 10,000 newtons. Okay, now in the end, it just asked how far does it travel. It really just asked for distance, didn't it? Distance is scalar, right? So even if I forgot the negative, would I be okay? Yeah, because if I got a negative number, I wouldn't make it negative when I wrote it down, hopefully. That's why I kind of made the big deal out of the negative here. I want you to get an answer that's got the right vector on it, even though it's not really a vector quantity. Okay, all right, so when we plug in our numbers there, okay, 0.5 times 1,700 times 36, okay, minus 0.5 times 1,700 times 20 squared, okay, divided by negative 10,000 newtons, 30.9 meters. Okay, ringing a bell? All right. So that's one with kinetic energy. Hey, anybody need that one anymore? Okay, this would be an example of one that's about potential energy. Anytime a question asks about height, is it asking about potential energy? Yes, okay, because that's the thing that affects potential energy, right? Mass, gravity, and height affect potential energy, and since gravity is always going to be the same, okay, we're basically always dealing with height for potential. All right, so we aim a slingshot straight upwards and draw it back 0.4 meters with a force of 1,500 newtons. Okay? The rock reaches a height of 30 meters. What's the mass of the rock? Okay, where are we assuming the rock's starting from? 0. So we're like, I don't know, laying on the ground with the slingshot, I guess. Okay, but we're assuming, since it doesn't say otherwise, that it started at a height of 0 because it's talking about a height here that's measured from the ground. All right. Okay, so we've got a force, we've got a distance, and we've got a height. Agreed? Okay, so our givens are, okay, distance 0.40 meter or 0.4 meters. Okay, that height is our final height, 30 meters. We can write that our initial height is 0. Okay, we don't have to write g, but we do know it. It's 9.81 meters per second squared. Right, and we're looking for the mass, and we also know the force was 1,500 newtons. Okay, questions so far? All right, so work's a change in potential energy in this case, and how much potential energy does it have initially? None. Not gravitational anyway. It does actually have what kind of potential energy when it's in the slingshot? Elastic potential energy, but we're going to calculate that by calculating the what? The work, yeah. When I pull that thing back, exert a force through a distance, I'm the reason that there's elastic potential energy in there, right? So we're kind of going to calculate that anyway. Okay, so we're going to have force times distance equals m times g times hf minus m times g times hi, which we just said was 0 anyway. All right, they want me to find the mass, so what do I have to move? G and h. Okay. Okay, so I just divide GHF over to the other side. Okay, that's going to leave me with mass. So when I plug in my numbers, okay, I'm going to have 1,500 times 0.4 meters divided by 9.81 times 30 meters. All right, it's a 2 kilogram rock. Everybody okay with that? Okay, ringing a bell? That's really all there is to it, guys. It's either going to be a kinetic energy change or it's going to be a potential energy change, and then the steps are pretty much the same. Okay, and we went over those steps. We had you write them down yesterday. Okay, so let's work on that worksheet, and we'll go over any ones that give you trouble. They do start out really easy. Okay, like it's just like force times distance. You don't even have to set it equal to any energy, at least at the beginning of that worksheet. Okay, and then it'll get kind of progressively more like these. Okay.